log in myself.
Oh, I see. Yeah. So when I start, how do you start the recording?
It's recording now.
Oh, is it?
Yeah, so basically there's one recording that will go through. Take the recording, chop it up.
Oh, right. Okay, so I just start.
You just start.
All right. Okay. Minutes. Right. There we go.
Try speaking.
Well, about to start. So,
Yeah,
all right. Okay, good evening everybody and welcome to Astronomy Education. My name's Colin Hill and tonight I'll be talking about terrestrial planets. So what is a terrestrial planet? Well, terrestrial, the word terrestrial means pertaining to the Earth. So a terrestrial planet is therefore Earth-like in composition, as opposed to a gas giant or a Jovian planet, which I'll be talking about the first lecture next year. So we'll get started. Okay, so as I said, terrestrial means pertaining to the Earth. And as I said, they are Earth-like in composition. So the four terrestrial planets in our solar system are Mercury, Venus, Earth and Mars. And this sort of shows you those four planets in a size comparison. So Earth is the largest of the terrestrial planets, followed by Venus and then Mars and finally Mercury. And Pluto gets a boot. It used to be classified as a planet, and if it was classified as a planet, it would be a terrestrial planet. But as I've tacked on a little bit at the end of this presentation to talk about dwarf planets, so I'll go into a bit more about Pluto. But back in the early 2000s, it was decided to demote it to dwarf planet status following the discovery of the dwarf planet Eris and several other large bodies out past Neptune in the Kuiper belt. So I'll talk a bit more about that a bit later. So just a little bit about planet formation. So the solar system formed by a large cloud of, or it's a nebula, a large nebula. Within that, there was some gravitational contraction, probably caused by a close-by supernova or a density wave travelling through the cloud. As it started to collapse, it gained some angular momentum and it started to spin and flatten out into a disk. So we ended up with something like this. So at the centre, where most of the mass was concentrated, there a protostar began to form. So this is like a the young sun in its early stages of formation. And around it is a circumstellar disk composing of hydrogen and helium gas, a few other trace gases, and lots of dust in the mix as well. So over millions of years, smaller bodies within the disk coalesced into larger ones, and until there are lots of planetesimals within the disk. There was a lot of debris also floating around. These continued to coalesce until it began to form the planets we see today. Now, farther out, it was cold enough for the outer planets to attract large atmospheres of hydrogen and helium. But for the inner planets, this was not possible, so they became the terrestrial planets. So if you have a look at a diagram of the solar system to scale, you can see that the terrestrial planets are all clustered around the sun here. So that's expanded out to Mercury, Venus, Earth and Mars here. These are the astronomical units of the distances out from the sun. Then we have the asteroid belt, and that sort of marks the boundary between the inner solar system and the outer solar system. And it's roughly where what is called the frost line. So beyond the asteroid belt, that's where gases can remain stable and don't get blown away by the solar wind. And that's why beyond the asteroid belt, we've got giant planets or gas giants beyond that point. So we'll start off with Mercury. So Mercury gets its name from the Roman messenger of the gods. It's the smallest, not only the smallest terrestrial planet, but also the smallest planet in the solar system. It's not a lot larger than the Moon, and in fact it looks a lot like the Moon because, like the Moon, it virtually has no atmosphere. You can see the distance from the Sun. It's about 0.39 astronomical units. And because it's very close to the Sun, it orbits fairly rapidly. So an orbital year is about 88 days to do a revolution of the Sun. But you can see the rotational period, or the day, is 59 days long. So there's not a lot of difference between a day and a year on Mercury. And it's actually locked into what they call a 3-2 orbital resonance. So for every 3 times it rotates on its axis, it rotates around the Sun twice. And it's locked into that resonance. Inclination, it almost spins vertically as well. There's very little axial tilt. And because of that, they believe that there's some ice trapped up in some polar craters, a bit like what they expect on the Moon. The mass, now we're using the Earth as a reference here. So if the Earth is 1, the mass of Mercury is 0.055. And the diameter, so it's about 1/3 the size of the Earth. Now, interestingly, the gravity is 0.39 of Earth, which is almost identical to the gravity on Mars, even though Mars is quite a lot larger planet. And the reason for this is Mercury is much more dense than Mars. And the reason for that is it has a very large iron core. About 70% of the mass of Mercury is the iron core. It does have a trace atmosphere, helium, oxygen, sodium. Most of this is probably derived from the solar wind because it doesn't have enough gravity really to maintain an atmosphere that close to the Sun. Being close to the Sun, as you can expect, it's fairly hot. And it is. It's about 430 degrees during the day, but it plummets to about -180 at night because of the nights are very long and there's no atmosphere to retain the heat. So we have a look inside of Mercury. As I said, the majority of the interior of Mercury is made up of the core. So there's an outer molten core and an inner solid core, but you can look at the size of it compared to the diameter of the planet. And they believe that when Mercury was forming, it was actually a much larger planet, and it got hit by a planetesimal during its formation, which stripped away a lot of its mantle, leaving a very large core but a very small outer layer above that. This is one of the features on Mercury, the Colaris Basin. It's actually it's an impact crater, but it's about a third of the diameter of the planet. So it's about 1,300 kilometres in diameter. So this is in false colour to try and bring it out a bit. But the impact was so severe that it sent a shockwave through the planet, and it erupted out the other side as a mountain range. So there's a series of mountains directly opposite the Colaris Basin, on the opposite side of the planet, caused by the shockwave of the impact. And then we move out to Venus, which is the Roman goddess of love. So both of those images there are Venus. So this one here is what Venus would look like if you looked out a window of a spacecraft. And this one here is a radar image taken by the Magellan spacecraft, which the radar energy can peer through the clouds. So it spent a year orbiting Venus and mapped the surface with radar. Because Venus is always cloaked in cloud, and you can never see the surface. So you can see the orbital distance. We're at the 0.7 AU. Now, this is interesting. It has an orbital period of 225 days, which is its year, but the rotational period is 243 days. So in this case, a day on Venus is actually longer than its year. But it's actually spinning backwards compared to all of the other planets. Venus rotates in the opposite direction, which is called retrograde rotation. It's a bit of a mystery why this occurred. It could have been by a large impact, which stopped it spinning and pushed it back the other way. We're not really sure. It has a mass similar to the Earth, just 0.8, and a diameter a little bit less than the Earth's, 12,100, as opposed to the Earth's about 12,700. So the gravity is comparable to the Earth's gravity. That's about where the similarity ends with the Earth, because if you have a look at the atmosphere, it's about 96% carbon dioxide, and the surface pressure is 90 bar. So that's 90 atmospheres at ground level. So that's equivalent to about a kilometre under the sea, if you can imagine that much pressure. And it's actually hotter on the surface of Venus than it is on Mercury because of the greenhouse effect of the carbon dioxide atmosphere. So the surface temperature is about 460 degrees, and that's day and night. Even at the poles, it doesn't vary much. It's about 460 degrees everywhere, all of the time. And those lovely white clouds you see there aren't clouds of water vapour, like on Earth. They're actually clouds of sulfuric acid. So if you could actually walk around on Venus, you would be crushed, baked, and dissolved, but not necessarily in that order. Not a very hospitable place. So you have a look inside of Venus. It's pretty much the same as the Earth, with the core, the mantle, and the crust. It doesn't have any appreciable magnetic field like on the Earth. Not quite sure why that is. It could be caused by the very slow spin, or it could be just the composition of the core. It might be completely solid and doesn't have the liquid outer core like on the Earth. It's the liquid outer core of the Earth that generates the magnetic field. I did forget to mention that Mercury does have a very, very small magnetic field, which is enough to deflect the solar wind around it. But Venus doesn't have that. Now, despite the conditions on Venus, we have actually managed to land there. The Russians did it several times back in the 70s and 80s. The probes didn't last very long on the surface. I think the one that lasted the longest was about 30 minutes before it succumbed to the conditions. So these are one of the few images ever taken from the surface of Venus. You can sort of just see the horizon over here. The conditions on the surface are like a very heavy overcast day on Earth. That's about the illumination. The visibility is not great. It's only about 1 kilometre or so because of the thick atmosphere. And it creates a bit of an optical illusion apparently on the surface, and it looks like you're sitting in the middle of a bowl with the horizon sort of curving up around you because of the optical distortion through the atmosphere. These are some of the images from the Magellan orbiter using the radar. So these are the volcanic domes on the surface. So there are lots of volcanoes on Venus, but they appear to be all extinct. There doesn't seem to be much volcanic activity. There's no tectonic plates, so it's reasonably inactive on the surface. And here shows a few impact craters. The only impact craters on Venus are very large ones. They don't find any small ones because anything that's small coming into that dense atmosphere just gets burnt up, doesn't reach the surface. So then we move out to the Earth. As you can see, the Terra in Latin. So Terra is where they get terrestrial from. So you can see there's lots of ones here because, as I said, we use the Earth as a bit of a reference standard. So it's 1 AU, 1 year, 1 day. Nothing much there that you probably don't already know. It has the strongest magnetic field of any of the terrestrial planets. One large satellite at the Moon, and it supports life. And the reason it supports life, we believe, is that the Earth is sitting in the middle of the Sun's habitable zone. So this is an area where a zone around the Sun or any star where liquid water can exist. And apparently it does encompass Venus on the inner edge of that zone and Mars on the outer edge of that zone. So if conditions were different on those planets, they could theoretically support life as well. So when we look at the interior of the Earth, as you see, it does have a double core. It has a solid inner core, and this is the liquid outer core, which apparently is responsible for the magnetic field of the Earth. Then we move out to Mars. So Mars is the Roman god of war. So it's a fair bit further out to 1.5 AU, but it's in a fairly elliptical orbit, whereas Venus is almost perfectly circular. It's the most circular orbit of any of the planets. Its rotational period or day is actually only a little bit longer than a day on Earth. It's 24.6 hours, and it's called a sol. And the inclination of the axis is similar to the Earth as well. It's just at 25.2 degrees, so it's just a little bit more than the Earth. So Mars does experience seasons, just like on Earth. But it's a fairly small planet. It's only about half the size of the Earth. But you see there the gravity, 0.38, where on Mercury it was 0.39. So they're almost identical, the gravitational fields on those two planets. Like Venus, the atmosphere is primarily carbon dioxide, about 96%. But whereas on Venus it was 90 bar, on Mars it's 6 millibar at ground level. So it's virtually a vacuum. However, there is enough atmosphere to give a bit of weather. There are clouds appearing sometimes, but it never rains because the atmospheric pressure is too low. and we get wind. In fact, the winds become so severe on Mars that they can whip up global dust storms that obscure the entire planet for weeks. Apparently, I was having a look at a video the other day. The dust storms on Mars, they're triggered by the trapped CO2 at the poles. When they come into summer, that CO2 gets released back to the atmosphere. And it's a fairly violent affair, and that's what triggers the winds that cause the dust storms. The dust is extremely fine. It's almost like talcum powder. So even though the atmosphere is very thin, it does manage to whip up the dust into the atmosphere, obscuring the whole planet. Now, the surface temperature is interesting. It can be in the middle of the day, especially near the equator, it can get up to 20 odd degrees, which sounds quite pleasant. But at night it plummets to about minus 150 because it doesn't have enough atmosphere to retain the heat. So the average temperature over the whole planet is about minus 63 degrees because it is significantly further from the sun. Now I mentioned the polar caps. You can see one of the polar caps here. Now the polar caps on Mars are a combination of water ice, which is permanent, and dry ice, which is frozen carbon dioxide, which is transient. So in the winter, the temperature at the poles becomes so cold, the atmosphere actually freezes out onto the ground. And then in the summer, it gets released back in the atmosphere again, which is, as I said, what triggers some of these dust storms. It has quite a few shield volcanoes, which are all extinct, and has a very large canyon across the face here called the Mariner Valley, which is the largest canyon system in the solar system. 2 small satellites, which appear to be captured asteroids, Phobos and Deimos. It appears that Mars did once support liquid water on the surface because there's a lot of evidence of dried up riverbeds and lakes on the surface, but it appears that there hasn't been liquid water on Mars for probably a couple of billion years or so. But there is a lot of water on Mars, all locked up in ice, not just at the poles, but even just subsurface ice. There is a negligible magnetic field as well, so there's a lot of solar radiation getting down to the surface of Mars, which is going to make it difficult for astronauts when they walk around on the surface. So Mars does have a reasonably large core as well. Not sure whether it's got a liquid core, but it's, even though it spins fairly fast, there's not enough there to generate an appreciable magnetic field. So these are some surface images of Mars. We've got some really nice pictures from the surface of Mars with all the rovers. This one here actually shows some clouds in the sky. The colour of the sky, though, is it's not blue like on the Earth, and it's not black like on the Moon. It's sort of a salmon colour. And this is as a result of those global dust storms I was talking about. Even when there aren't any dust storms, there's always dust in the upper atmosphere. It's so fine it never really settles. So it gives the sky a permanent salmon colour. As I said at the start, I was going to talk a bit about dwarf planets because they're sort of like terrestrial planets, so they're small rocky bodies. So the dwarf planets, they came about in the early 2000s, about 2004, I think. This was several years after they discovered Eris. Now, Eris was, at the time, was thought to be a little bit larger than Pluto, but much, much further out. And so that was a bit of a dilemma, you know, do they make Eris another planet, or do they make Pluto not a planet? And then they started finding some other bodies out past Neptune as well. And it became apparent that there's actually a large asteroid belt out past Neptune. It's called the Kuiper Belt. And it just appears that Pluto and Eris just happen to be probably the largest members of the Kuiper Belt of asteroids. So they came up with a definition of a dwarf planet as opposed to a traditional planet. So like a traditional planet, it has to orbit the sun, and it has to have sufficient mass for its self-gravity to assume a near spherical shape. And that appears to be around about 400 kilometres. A body has to be around about 400 kilometres in diameter to sort of pull itself into roughly a sphere. And this is the clincher here. It has not cleared the neighbourhood around its orbit. So because it's an asteroid belt, it's sharing its orbit with other bodies. So that's what sort of sets it apart from a regular planet. And of course, it's not a satellite. So that's why Ganymede's not a planet, because it's a satellite and not a planet. We've also got one dwarf planet which is not in the Kuiper Belt, and that is Ceres here. So Ceres is the largest main belt asteroid. So if you have a look here, it's here. So Ceres was actually discovered in about 1801, and initially they thought they'd actually discovered another planet, and for about 80 years it was treated as a planet until they started finding other objects in the main asteroid belt, and then they realised that it's just the largest of a whole swarm of asteroids. So there's a picture of Ceres that's been visited by the Dawn spacecraft. And also Pluto has also been visited as well. And Pluto does actually have a family of moons. It's got about 5. The largest being Charon, which is about half the size of Pluto. And there's also Kerberos, Styx, Nix and Hydra as well. And this is a picture of Eris. And it also has a moon called Dysmonia. But it's much, much further out than Pluto. I just remember when they discovered Ceres, you've heard of the Titus-Bode law. It was sort of a mathematical sequence that explained where the planets lie in their distance from the sun, and according to that law there should be a planet in the asteroid belt, and when they found Ceres they thought that was the planet that fitted into that law. It does look like a planet probably tried to form there, but Jupiter's gravity disrupted the process, and all the material got just strung out into a ring around the sun. Even so, if you could get all of the asteroids in the asteroid belt and compress them into a solid body, it would still be only about the size of our moon. So this is the orbit of Eris. So you can see when Eris was discovered, it's almost as far from the sun as it can get. So there's the orbit of Pluto here, and you think Pluto's a long way out, but Eris is about twice as far out again. So the Kuiper Belt is a very extensive belt around the sun. It's also highly inclined to the plane of the other planets, a bit like Pluto. That's another reason why Pluto and Eris sort of stand out differently to the traditional planets, in that it's a highly elliptical orbit and very inclined to the plane of the other planets. So this is the largest dwarf planets that have been discovered in the Kuiper Belt to date. It does appear that Eris is a little bit smaller than Pluto, but it's only by tens of kilometres. They're almost identical in size. You can see there's Charon. It's almost a dwarf planet in its own right. It's actually bigger than some of the other dwarf planets that have been discovered. But there's the scale there. That actually is the end of the talk. Bit of a quick one today. Any questions? Must have covered it pretty... Yes, Peter. Planet X. I've seen a few things, but yeah, they do believe that there could be a large regular planet out, probably in the Kuiper Belt somewhere. But it has so far eluded detection. But a lot of people are fairly confident there is something out there. How big it is, whether it's a terrestrial planet or a gas giant. You think if it was a gas giant, they would have found it by now, wouldn't you? No. It's Germany. I don't think it goes that far, but I think it goes to the inner edge of the Oort cloud. Yeah, the Oort cloud. Yeah. Yes, so the Oort cloud is a theoretical suppository of cometary bodies, but that's extends out to about 1 light year. They reckon the outer edge of that. So the Kuiper Belt sort of sits within between the Oort cloud and Neptune. So there's probably a lot of undiscovered objects in the Kuiper Belt as well. Any more questions? Okay, thank you very much.